Welcome everyone to the final video of this week. So for the do now today, you can go to the slides yourself and click the video if you'd like, but also try to play it here. Think about what variables are changing. Alright, so that was a little preview of today's third and final gas law, or for this week at least. Gay-Lussac's law, so 3.11. So you may have realized volume was not changing there because the Erlenmeyer flask was a constant volume. So today we're going to be talking about how do pressure and temperature relate to each other. So what's happening in the demo that we just saw is that as the gas inside the flask cools down, the pressure in that flask also decreases. So you have low air pressure, and the egg gets sucked in because it's lower pressure. The high pressure is pushing it down into the flask, or even pushing it up into the flask, just because inside the flask it's a weaker arrow, less pressure than outside. The molecules are bouncing on this egg and forcing it inside. So Gay-Lussac's law says that pressure is directly proportional to temperature. Again, you want to make sure the temperature is written in Kelvin, otherwise the math won't work out. So why is this true? Remember that pressure is about how much gas molecules hit the walls of a container. So if you change the temperature is a measure of kinetic energy. So you're giving, let's say you increase the temperature, you give things more kinetic energy, then they're going to bounce off the walls more, and then that leads to increased pressure. So therefore, they're directly proportional so long as you keep the volume constant. You have to keep the volume constant. And so the formula for Gay-Lussac's law is P1 over T1 equals P2 over T2. It looks really similar to Charles's law because, again, volume and temperature are directly proportional, so are pressure and temperature. So as a recap, we have these three gas laws: Charles's law, Boyle's law, Gay-Lussac's law. All of them relate two of these three variables, and the third one has to be kept constant. If the third one's not constant, then you can't use these formulas. Next week, we're going to talk about how you can even combine all these and take the number of moles of the gas into account. So you kind of see as a preview, they all come together to form the combined gas law, from which you could derive any one of these. But different people kind of discovered each of these parts independently. For now, though, just worry about these three. Alright, and finally, we have a check-in. I'll leave this up here. You can press pause and work on it if you'd like. Or you can also open up to the gas law practice problems, the practice quiz at this point, maybe even tackle the formative assessment for this week. Alright, best of luck with that. See you all either during office hours or hopefully in the coming weeks.